Good evening to all. Today we are going to discuss about thermodynamic process for constant volume used for the real gas applications. I am sure this video is going to be very interesting, so please do keep watching until the end and subscribe my channel. Thank you. So let's begin the discussion for thermodynamic process for constant volume for real gas. Before that, let's understand thermodynamic system. Thermodynamic system, as I said, as we know that it is related to only the gas. So our focal point is only gas, not the compressor, not the turbine. So there is a sign convention when heat transfer, that is heat is given to the thermodynamic system. That means gas, it is considered positive. When heat is taken from the system, it is negative. When work is done by the gas is positive, when work is done on the system is negative, and energy transfer or energy level when increases of the gas or the system is positive, when energy level decreases of the system is negative. These are the sign convention. And types of thermodynamic system is open system, closed system, isolated system. In case of open system, there is a flow of the gas. You can see flow in and flow out, and also there is a heat energy transfer. In case of closed system, there is no flow of the gas, so gas transfer, mass transfer doesn't occur, only transfer of energy. In case of isolated system, neither mass transfer occurs nor the energy transfer. Real gas equation of state is PV is equal to ZnRUT. On simplification, we can write PV is equal to P small v is equal to ZRT. This is most important equation. This can be used for derivation purpose. For all details are given. What does stands for P small v ZRT? Z is a compressibility factor. Work transfer on the closed system, which is also shown on the PV diagram. Area under the curve on x-axis is called the is equal to the work transfer, and which is defined as P for the closed system is integration of PdV. In case of open system, it defined as minus VdP, and area under the curve on y-axis, that is in PV diagram pressure axis, is equal to work transfer for the open system. As per sign convention, work done by the system is positive and work done on the system is negative, and work transfer per unit mass is called work head or head. Similarly, energy transfer for the closed system is equal to internal energy change, and which is defined as integration of CVDT. So energy transfer for the closed system is equal to integration of CVDT. Similarly, energy transfer for the open system is equal to enthalpy change, and which is defined as a integration of CPDT. So we can write energy transfer for the open system is integration of CPDT. Energy transfer or energy of system, if increases it is positive, and decreases it is considered negative. This is as per the sign convention. As per the first law of thermodynamics, the heat transfer is equal to work transfer plus energy transfer, which is Q is equal to W plus V. And very important information for first law of thermodynamics says that, or assumes that, the efficiency of thermodynamic machine is 100%. That means there is no losses of during work transfer, heat transfer, energy transfers. So process is considered idle and efficiency is 100%. With that assumption, this equation is valid. Heat transfer is equal to work transfer plus energy transfer. Now the constant volume process, which is also called isochoric process, which is shown on PV diagram and TS diagram. On PV diagram, you can see 1 into 2 heat is added, and this 1 and 2 is heat is removed. So on TS diagram, temperature entropy diagram, 1 and 2 is heat is temperature increases, entropy increases, and below this 1 and 2 heat is removed, so in temperature drops and entropy drops. Now work transfer for the closed system, we can write, so volume is constant, so your PdV is work, and you can also see in this process on PV diagram area under the curve on x-axis 0. That is why you can also see here as per formula is 0, and this is also you can see the 0. So work transfer per unit mass is 0, so work total mass is also be 0. Energy transfer is a CVDT for the closed system, so we can write energy transfer per unit mass is CV. into T2 minus T1, and for total energy transfer just multiply with mass m into CV T2 minus T1. Heat transfer, this is as per first law of thermodynamics, Q is equal to W plus E. So since W is 0, we can write Q is equal to CV T2 minus T1. So heat transfer per unit mass, we can write CV T2 minus T1. For total heat transfer, just multiply with mass m. So we can write m CV T2 minus T1. Area under the curve on TS diagram on x-axis is equal to heat transfer. You can see this much is heat transfer for the process 1 and 2. Now constant volume process in open system. For the area under the curve on y-axis, it will be equal to work transfer. So volume is constant, V is equal to V2 V2, and real gas equation PV is equal to Z RT. So P1 V1 Z1 RT1, P2 V2 Z2 RT2, and as per formula W is equal to minus VD PE. So just V is constant, so write V1 P2 minus P1. So we can write V1 P1 minus P2. Just we can write W is P1 V1 out 1 minus P2 by P1. But P1 V1 can be replaced at Z1 RT1. So W is equal to Z1 RT1 into bracket start 1 minus P2 by P1. This is expression for work transfer per unit mass. If you want to calculate total heat transfer, just multiply. Sorry, work. If you want to calculate total work transfer, just multiply mass of this. This is m Z1 RT1 into 1 minus P2 by P1. This is expression for total work transfer. You can see the work transfer is shown on the PV diagram. Area under the curve on y-axis, that is on pressure axis. This is equal to work transfer. Now energy transfer, we know this is open system is a CPDT. So we can write CP T2 minus T1. For total energy transfer, just multiply with mass m CP T2 minus T1. Again, as per the first law of thermodynamics, heat transfer will be what W plus E. So just Z1 RT1 bracket start 1 means P2 and P1. This is for work, and plus Cp T2 minus T1. This is for E. So this is total is the heat transfer per unit mass. For total, just multiply m with this large equation. This will give the total heat transfer. Heat transfer is shown on TS diagram. You can see on the process 1 to temperature entropy diagram. Area under the curve on x-axis will be equal to heat transfer. Now let us understand with an example for constant volume process for closed and open system. And nitrogen gas has initial pressure and temperature R 0.5 bar gauge and 30 degrees Celsius respectively. Heat is added to thermodynamic system such that the final pressure reaches to 0.8 bar gauge on constant volume process. With the consideration of real gas, calculate work, energy transfer and heat transfer during this process for considering the closed and open system. Also calculate the inlet specific volume. Following data are given: mole weight of nitrogen 28, universal gas constant 831.5, specific heat capacity at constant volume, constant pressure or 20.89 and 29.26 respectively, compressibility factor at inlet and final R 0.99 and 1 respectively, and local barometric pressure is 1 bar absolute. So now inlet data is given: temperature, local barometric pressure. So absolute pressure P1 is calculated by adding local plus, that is 1.5, temperature 30, and P2 is again added this mole weight, everything is given, Cp, Cv all are given, Ru is given. So we can write converting gas constant Ru by m, and also converting this, in the joule per kg per Kelvin, just dividing by m, multiply 1000. Cp calculated, then K can be calculated, and V is equal to Z1 R T1 P1. T1 is a absolute temperature which is added to 73.15 with the gauge in this equation, and P1 multiplied 10 to the 5 to convert in Pascal. So it is coming 0.6. T2 outlet in degrees Celsius 90.3, work transfer is 0, energy transfer is 44,963, and so heat transfer will be same 44,963 joule per kg Now the open process is work transfer is 17 minus 17,986. Energy transfer is 62,978. So work transfer, sorry, heat transfer is just add these two, it is 44,992. So I hope you have enjoyed this session. Thank you. Thank you for watching.